Alright, last time we talked about the general features that you can measure on a graph. We talked about position versus time graphs, or displacement versus time graphs. Now we're going to move on and talk about velocity versus time graphs. So I'm just going to line this off so we don't get everything mixed up. Okay, and again, first thing I'm going to do is measure the slope and the area. So we draw a best fit line. That looks good. This pen is really starting to blot. I don't like that. Okay, so first thing we'll do, let's measure the slope. Okay, and again, we're going to pick points that are right on the line itself. Let's see here. I'm going to pick this one and this one. These look good. So remember, slope is y2 minus y1 over x2 minus x1, and because this is not a position versus time graph, this is a different graph altogether. And by the way, these two graphs are not related in any way. They're two completely separate things. The slope is going to tell us different information this time, and all of our questions are going to have different answers to them since we've changed what type of graph this is. So let's make this point 2 and then point 1. y2 looks to be about 16, and the units are meters per second because this is velocity versus time. y1 looks to be about 28 meters per second. And the x-coordinate's a little bit easier, 8 and 4. 8 seconds minus 4 seconds. Make sure you don't flip-flop those by accident. 16 minus 28 is negative 12. Divided by 8 minus 4 is 4. So divided by 4, we get a slope of negative 3. And the units, be very careful with the units. Meters per second, and then you divide another seconds into that. The second, so you could write it like this, meters per second, or you could always do, you could think of it this way, meters per second, we have another second on the bottom. Dividing by a second is the same as multiplying by 1 over seconds, which gives us meters per second squared. So the slope here is negative 3 meters per second squared. And we'll talk about what that is in a little bit. The area. Again, we have a trapezoid shape, but we're not going to deal with the area formula for a trapezoid. We're simply going to split it up into a triangle and a rectangle. So the area of the rectangle is base times height. The base is 10 seconds. The height seems to be, let's see, that ends about 10, so yeah, 10 meters per second. And let's see, that would be 100. If we have seconds on top over here, multiplied by meters over seconds, we have seconds on top, seconds on the bottom, those cancel out, we just get 100 meters. The area of the triangle, on the other hand, is 1/2 base times height. 1/2, the base is still 10 seconds, not meters. And the height, it goes from 40 to 10, so that would be 30 meters per second. 1/2 of 10 is 5, 5 times 30 is 150. The total area of the rectangle plus the area of the triangle equals 100 meters plus 150 meters, and that would be 250 meters. Okay, so there's the calculations, and again, we'll come back to those calculations as we go. We're gonna look at the 3 essential questions again. So we're gonna look at those 3 questions and see what the and see how the answers differ for this as opposed to the x versus t graph. So question number 1, is the y variable positive or negative? In this case, it's a little, people can miss this, but the y variable is always positive here. All the data points are above the x equals 0 line. So I would say the velocity is always positive. In other words, if the velocity is always positive, that means the object is always moving forward. That's what positive velocity means, right? Okay. So if the velocity is always positive, the object always moving forward, then one of the things that I want to point out is that on a v versus t graph, to find v at some point on v versus t graph, all you have to do is look at the y coordinates. Now this is different from the x versus t graph. The x versus t graph, looking at the y coordinates, told you the position. Now it tells you the velocity. You might say, well, that's a very obvious thing, but people miss that sometimes. Question number 2, is the y variable increasing or decreasing, / is the slope positive or negative? Remember, those two questions are linked. It's really the same question. The y variable here is very clearly decreasing. Starts up at 40, goes down to 10, which is the same thing as saying the slope is negative. So I'm going to say the v, the velocity, is decreasing / the slope is negative. Okay, so that slope is negative. Now, we're going to come back to that in a little bit, and we know the slope is negative because we found it up here. And also notice that that slope being negative, the slope has units of meters per second squared, and hopefully you remember what those units mean. Those are the units of acceleration. And if you think about the definition of slope, the change in one thing divided by the change in the other, the change in y, which is velocity, the change in velocity divided by the change in time, that's a definition of acceleration, the rate of change of velocity divided by, or over time. Okay, so it makes sense that the slope is the acceleration. So here, on this particular type of graph, the slope tells the acceleration. On a v versus t graph. So in this case, it's actually kind of interesting that it tells us that the acceleration is negative because the slope is negative. Okay, so the acceleration is negative. In other words, the velocity is changing to be closer to negative infinity. That's one of the best ways I can think of. If you're looking at the velocity and it's trending one way or another, that tells you if the acceleration is positive or negative. The velocity is becoming, it's getting more and more, even though the velocity is positive right now, it's getting closer, it's getting farther away from positive infinity, it's getting closer to negative infinity. So we say that the acceleration is negative here. Question number 3, is the value of the slope increasing or decreasing, / is the slope getting more or less steep? So I would say that here, I mean, we still have a case where the slope itself is constant. The slope is not changing. It's a negative slope, but that does not mean it's a slope of 0. Okay, it's a negative slope. It is not changing. So slope is constant. So we know that the acceleration is constant, which just means the acceleration is not changing. And if you think about it, a lot of the stuff we do is constant acceleration stuff. So let's see here, what else did I want to talk about? Okay, so yeah, the slope is constant, so the acceleration is constant. Okay, and that's actually all I want to say with that one. The one other thing I did want to point out, since we've got that the slope tells us the acceleration, what does that area tell us? Well, if we look at the units for area, it tells us that it has units of just meters. So what this is actually telling us on an A versus T graph, area is actually the displacement over a period of time. Okay, and you can actually you could actually determine this for yourself. You could say, okay, well, let's see, the area is 250 meters, so that means it traveled 250 meters during this time. If you were to actually plug these numbers into one of the kinematics equations, let's say the initial velocity was 40, the final velocity was 10, the acceleration was -3, and solved for the area, that would be, maybe I'll just sketch it out to the side here, v squared equals v naught squared plus 2ax minus x naught. Let's see here. Let's assume that x naught is 0. That's 10 meters per second squared. That's 40 meters per second squared. Plus 2 times -3 meters per second squared. X. 10 squared is 100. 40 squared is 1600 minus 6x. 100 minus 1600 is negative 1500 divided by negative 6. We get 250. Oh, 100 minus 1600 divided by 6 negative. There we go, 250. So it works out. We find the displacement was 250. The one thing that you cannot find for this, okay, so I'm just going to put a note. Without actually knowing x naught, we cannot determine the exact position. Now, I said over here, let's just assume it's 0, but we're not told that. It could have started at negative x equals negative 2. It could have started at x equals positive 187. We don't really know, okay? But the key here is that unless we're told the initial position, we actually cannot find that from this graph. There are some things that you just cannot find from certain graphs, okay? And that just happens every once in a while. Oh, my paper is really curling up. All right, so anyways, that's a v versus t graph. If you look at the y-coordinates, that tells you the velocity. If you look at the slope, it tells you the acceleration. If you look at the area under the curve, that tells you the displacement over a certain period of time. You cannot determine the exact position, but you can determine the displacement from where the object started, okay? And for most of these v versus t graphs, we will see constant slopes representing constant acceleration. Let's now go to the last of these. Let's go to an a versus t graph. Okay. Let's just get this centered. Okay, there we go. So, for an a versus t graph, this is kind of a weird shaped graph, and I did this for a reason. Let's make the best fit line here. You'll notice that my best fit line is kind of weird. It is very flat in the beginning, and then it seems like it immediately jumps straight down, and then is flat down here as well. So this is a graph that actually, it would never happen exactly like this in real life, but I'm making a little bit of a simplification. In real life, you would never have an acceleration instantaneously jump from one thing to the next. That's impossible. It would have to happen over a time period. But since we are trying to make things as simple as possible, as basic as possible, you can have an acceleration that changes very, very rapidly. You would just never have a straight down line like this. So it's fine to approximate that this is more or less what happens. Okay, let's talk about the slopes. I'm not even going to calculate the slopes here. I'm just going to tell you what they are. Okay, so the slope from, let's say, 0 seconds to 8 seconds is very obviously 0 meters per second, and it's meters per second cubed, because you would take meters per second squared, divide by seconds, which is the same as taking meters per second squared and multiplying by 1 over seconds. You get meters per second cubed. Okay, so the slope from 0 to 8 seconds is 0 meters per second cubed. The slope from 8 to 10 seconds, that's another flat line, so that's also going to be 0 meters per second cubed. And if you're confused why it's 0, think about what you'd get if you plugged in the slope calculation. You have the same y coordinate the entire time, so the top would end up being 0, the bottom would be, well, not 0. So you would have some, you would have, when you did the math, you would get 0. The slope at 8 seconds, we would actually call that undefined. And again, this can't really happen in real life. But that slope would be undefined, because that would be a change in acceleration over no time at all. And again, in reality, that doesn't exactly happen like that, but we can approximate here. Okay, so there's the slopes. All right, so slope of 0 meters per second cubed, which is a little strange, and then the slope at 8 seconds is undefined. Let's do the areas. So remember, it's the area between the graph, the data points, the best fit line, and the x-axis. It's not just to the bottom. Notice our x-axis is actually right here for this graph at 0, because the x-axis is always at x, where y equals 0. So we split this into two shapes. We got this big shape right here, and also a little smaller rectangle right there. So I'm going to label this 1 and 2. And the area of 1 is base times height. The base is 8 seconds. And the height seems to be about 6 meters per second squared. Now remember what acceleration is. It's the change in velocity over time. What an acceleration actually tells you is the amount of change in velocity per a second, per 1 second. So if you have an acceleration of 6 meters per second squared, that means your velocity will change by 6 meters per second every second. We're going to come back to that. So the area there is 48 meters per second. I'm going to put a positive sign there. For number 2, our base is, let's see here, our base is 8 to 10 seconds. That's 2 seconds. And our height, it's kind of a negative height, is negative 2 meters per second squared. And 2 times negative 2 would end up being negative 4 meters per second. And if we want the total area, well then very simply it would be 48 meters per second minus 4 meters per second equals positive 44 meters per second. All right, so those are the areas. Let's look at those. That's the slope in the area. Let's look at those questions. Question number 1. Question number 1, is the y-coordinate positive or negative? And the answer to that is, well, a little bit of both. From 0 seconds to 8 seconds, the acceleration, because that's what we're measuring here, is positive. And then from 8 seconds to 10 seconds, it is negative. Okay? So on an acceleration versus time graph, to find the acceleration, look at the y-coordinates. You might say, well, what is it at 8? Is it positive or negative? Again, this is a case where that wouldn't actually happen in real life. You wouldn't have 2 data points showing 2 different accelerations for one object for 8 seconds. That wouldn't happen in real life. Okay, it would be a very, very steep downward slope, but some time would pass between the acceleration of 6 meters per second squared and negative 2 meters per second squared. Question number 2. Question number 2, as a reminder, is the y variable increasing or decreasing? Or, in other words, is the slope positive or negative? We kind of answered that up here. The slope is 0 meters per second cubed at all points except 8 seconds, which is where it is undefined. And as a reminder, it's equivalent to saying that the slope is essentially 0 at all those points. The slope is 0, which means the acceleration is not changing. By the way, the change in acceleration over time would be referred to as jerk. And it is a real thing. You can actually measure the jerk of something if there is, for instance, a changing force pushing on something that would cause a changing acceleration. You can measure the jerk. You can even measure the change in jerk over time and the change in that over time and go down this nice rabbit hole of how all these quantities change over time. The next terms after jerk are somewhat humorously referred to as snap, crackle, and pop, but we won't really get into talking about those. And we're not even going to talk about jerk. We pretty much exclusively deal with constant acceleration. Okay. All right, the answer to the last question. Okay, so number 2, the slope is 0. If you really want to know, the slope of acceleration versus time graph tells us the jerk. And then number 3 is the value of the slope increasing or decreasing. Obviously, it's 0 here, it's 0 here. The slope is staying the same except at this one point. So I guess I could say here, the slope isn't changing except at 8 seconds. Okay? So the important thing for a acceleration versus time graph, to find the acceleration, you look at the data points. The slope isn't going to tell you anything super useful. It tells you the jerk, but that's not really something we're going to study that in depth. But one other thing that's interesting is look at the units on the area. The units are meters per second. And that should tell you this has something to do with velocity. Remember when I said that an acceleration tells you how much the velocity changes per second? If you have an acceleration of 6 meters per second squared, that means your velocity increases by 6 meters per second every second that acceleration exists. This acceleration exists for 8 seconds, so you would expect the acceleration to change by 6. Okay, so 6 to here, 6, 12, 18, 24, 30, 36, 42, 48 meters per second. And that's exactly what we find for the area here. If you have a negative acceleration of -2 meters per second squared, then that means that your velocity should decrease by 2 for each second that it has that. So we have a total negative a change in velocity here of -4. We combine the two. We find the total area, accounting for both of these, and this has a negative area, is positive 44 meters per second squared. What that tells us is that for an A versus T graph, area under curve tells us about the change in velocity over a time period. Okay, and I'm going to stop there. Those are the big facts that you need to know for these different types of graphs. We've gone over position versus time, we've gone over velocity versus time, we've gone over acceleration versus time. For each of those, there's somewhere between 2, 3, 4 facts that you need to know about how to read those graphs, how to figure out the position, how to figure out the velocity, how to figure out the acceleration, things like that. By the way, in this graph, there is no way to tell position or I guess I'll say actual position or actual velocity unless x naught and v naught are known. So the use of those facts is going to be very important as you continue to get better and better at reading graphs. When we come back, we'll look at a couple more types, this more complex graph. We'll also look at predicting what other graphs should look like.